1.5. So in section 1.4, you notice that, well, we had this lurking concept of a limit lurking in the background. Actually, it wasn't lurking in the background. It was in the forefront. It was right in front of your face, slapping you in the face, and you really can't ignore it. And so we really have to discuss this limit, idea of a limit, a little bit more. It may be a little bit more problematic than you think. This concept of a limit took shape, really, it took over 2,000 years before people really understood what's going on. So the idea of a limit really started back in Archimedes. So back with the Greeks, ancient Greeks, and they really weren't able to comprehend this concept. And it took until Cauchy in the 1800s before they really understood what was going on. Cauchy, Weierstrass, people of that sort. So this will be a first sort of attempt to give you an idea about the concept of a limit. In section 1.7 and 1.6, we'll give you more detail behind this. So suppose I have some function relative to some coordinate system. So the function y equal f of x. This function y equal f of x looks like this, but it has a hole here. And at a, it's equal to this value up here. So notice that all of a sudden, the curve goes from this point here and jumps up to this point. And then it continues on. So it's nice and smoothly going along here. And then it jumps up here, jumps back down, and then continues on. Okay. So that's what the function looks like. And suppose that I want to determine the limit as x approaches a of f of x. Well, as x approaches a, so as I get closer and closer and closer to a, if I look at my y values are getting closer and closer and closer. Let's go from both directions to the value L. So as x gets closer and closer to a, my y values keep getting closer and closer to L. So therefore, we say here that the limit as x approaches a of f of x is equal to L if as x approaches a, f of x approaches L. And so as we get closer and closer to a, if my x values keep getting closer and closer to a, if my y values are getting closer and closer to L, then we denote that by the limit as x approaches a of f of x is equal to L. In other words, we can make f of x as close as we wish to the value of L by choosing values of x that are sufficiently close to a, but not necessarily equal to a. So we keep getting closer and closer. I keep taking numbers that are closer and closer to a, but not necessarily at a. Because at A, we're way the heck out here. But near A, we are closer and closer to L. So we keep getting closer and closer to it, but we really don't care what happens at the point A. So what happens at A, I don't care. But I do want to approach A from values both smaller than and greater than A. So let's do an example. So now I want to determine the limit as x approaches 0 of the following quantity. The square root of x squared plus 4 minus 2 over x squared. Okay, so we can just plug this into a calculator. So I'll do that. So I'll just plug in 1 into my calculator. If I do that, well, my y value becomes 0.2360797775. If I plug in -1, well, I get the same answer because this is symmetric about the y-axis. So -1 will give us the exact same answer as what I got for 1. So at -1, y is 0.23606797775. Same value. So I really only have to look at positive values because for the negative values, they'll give me the same answer. So now let's plug in 0.5. So if I plug in 0.5, I get a bigger number. Notice it goes from 0.236 to 0.246. So I get 0.24621125512. Okay, well, this is going to take me forever. So why don't I take a number like 0.000001, plug that into my calculator. This was done on a TI-83. And so when I plug that into my calculator, I get 0. So what the heck is going on? So if you take numbers getting closer and closer to 0, they keep getting bigger and bigger, except all of a sudden they drop down to 0. And as a matter of fact, when you take smaller numbers, like let's take this has 1, 2, 3, 4, 5 zeros. So take 6 zeros and a 7. You'll still get a 0 here. So what do you think the answer is? So what is this limit? When you plug into your calculator, you get something getting bigger and bigger and bigger, but then all of a sudden it drops to 0. So what do you think your answer is? Anyone? If you don't want to say it out loud, you can always just type in the chat box. What do you think?
0.
What sort of value is? Yes. So what's the limit? Anyone?
0.
0. Okay. Everyone thinks it's 0. Anyone think anything different?
No. Dividing by 0 will be like infinity or something.
Infinity. So people think infinity. So 0, infinity. Okay. Remember, you don't actually go to that. Here, let me close this.
So it would be infinity then.
So
Or
remember, you
undefined.
never actually plug in the value here, right? Here, let me get my calculator again. So if you plug in, oops, sorry. If you plug in if you keep plugging in numbers, did this, here, wait. Because did I have to do a screencast again? Yeah, I have to. Sorry. Okay. Yeah, as you keep getting closer and closer to 0, well, let me plug in here. Let me plug in. It'll take me a second here to put in the actual question. It's the square root of x squared plus 4 minus 2 over x squared. Okay. So let's plug in another number. Let's say 0.3. If I plug in 0.3, I get 0.24861 860,935. So actually here, maybe I'll write on this for a second. Do this in, why has it gotten rid of it? Okay, so let's get some more. If I plug in 0.3, I get 0.048609351286. If I plug in 0.001, if I plug in 0.001, I get 0.25. Exactly. If I plug in 0.0001, because I led you guys astray, it's 0.25. What do you think the actual answer is? What do you think the limit is? And so if you plug in 0.00001, you get 0. But if you plug in 0.0001, you get 0.25. So what do you think the limit is? Anyone? 2 to the power 12. Ooh, that's a big number. Ooh. Okay, so it turns out it's actually going to be 0.25. But it's not so obvious. So the answer is you can't really do these type things by just plugging in numbers. You would think, so the answer is you can't trust your calculator. It turns out that the reason I put in the 0.0001, because your calculator gives the wrong answer. So it's not that. So the problem is, and I don't think anyone noticed this, everyone had faith in the calculator. The calculator is wrong. So the problem is your calculator is wrong. And so you're plugging in something and you're being led astray by the fact that your calculator is wrong. Okay. So I guess the moral of the story is don't believe your calculator. It gives you wrong answers. And so that's why all of a sudden you were thinking, well, it's equal to 0, it's equal to infinity, it's equal to etc. Because your calculator is just not is leading you astray. So this is a little bit more subtle than you think. So we're going to have to study this some more because some weird things are happening here. If I can't trust my calculator, what can I do? I mean, plugging in numbers and seeing what it approaches is not really helping me. This is giving me these are leading me to incorrect assumptions, incorrect answers. This is not the correct way to proceed. So I'm not going to do this because I am being led astray. So let's do something else. So first off, let me give you some additional concepts. And so this concept that I gave you at the beginning is called a two-sided limit. And so because I was approaching from both the right side and from the left side. So let me give you a concept where I only approach from one side, what's called a one-sided limit. So let's look at a one-sided limit. Again, I'll have the same sort of function. So I have the graph of y equal f of x. So it looks like this. And then at A, it jumps up here. Then past A, it looks like this. So that's the graph of y equal f of x relative to some coordinate system. And so here's my y value m and my y value n. The right-sided limit, sometimes denoted by the limit as x approaches a, but notice there's this superscript here of a plus sign. This indicates that I'm approaching from the plus sign. So from the plus side. Well, the plus side, well, for the x-axis, where are the pluses? The pluses are on the right. And so I'm approaching from the right. So this is called a right-sided limit. Sometimes we use this symbol to indicate a right-sided limit. We're taking values of x that are bigger than a and approaching a. So there are values of x here that are approaching a, and they start from x's greater than a. And so we're starting here and then going down to a. So that's why this indicates this direction, where we're taking big numbers here and approaching a smaller number here. So if we can make f of x as close as we wish to n by taking values of x sufficiently close to a, with x being greater than a, then we say that the limit as x approaches a from the right side of f of x is equal to n. Similarly, and now let's do it from the left, we'll denote the left-sided limit as follows. The limit as x approaches a from the left side of f of x is equal to m. Remember the picture, I'm approaching m here. Or the limit as x approaches a, taking values of x that are less than a of f of x is equal to m. If we make f of x as close as we wish to m by taking values of x sufficiently close to a with x being less than a. So that's the concept of a left and right-sided limit. Note the following. That the limit, the two-sided limit, the limit as x approaches a of f of x is equal to L if and only if the right and left-sided limits both exist and are equal, and the mutual value that they're equal to is the value of the two-sided limit. So the limit as x approaches a of f of x is equal to L if and only if the limit as x approaches a from the right side of f of x is equal to the limit as x approaches a from the left side of f of x is equal to L. So if both the right and left side of limits exist and are equal, then the two-sided limit exists and is equal to this mutual value. Let me discuss the infinite limit. Some people were talking about infinite limits, even though they didn't know that they were talking about infinite limits. And so, by the way, in general, for all these limits, we're always divided by something going to zero. So almost always in all these limits, we're divided by something going to zero. So if you plug in zero, you always get that it looks like you're going to infinity or something, but you're not. It's a limit. It's Zeno's paradox. You are hitting Zeno. So you're hitting the paradox that Zeno got to, that all of a sudden you think it's taking you an infinite amount of time and it's not. It's a limit. Well, this is why it took 2,000 years. So it's not that obvious. And for 2,000 years, everyone else in the world had a hard time with the concept. And so let me talk about infinite limits. So suppose I have some function here, and as you approach A, all of a sudden it goes off to infinity. It keeps getting bigger and bigger and bigger and bigger. Well, and suppose that this is from the left side. Then we will say that the limit, so in this situation, we say that the limit here as x approaches A from the left side of f of x is equal to plus infinity. Or we use this notation. The limit as x approaches A, again from the left, for values of x less than A of f of x approaches infinity. So this is true if we can make f of x as large as we wish by taking values of x sufficiently close to A with x being less than A. Okay, so I think the rest of these I'm just going to do by picture. So suppose you have some function here and it goes off to infinity at A for values of x bigger than A. Then we denote that by the limit as x approaches A from the right side of f of x is equal to plus infinity. Or the limit as x decreases down to A of f of x is equal to infinity. Suppose we go to negative infinity. So suppose I have some function, and as you get closer and closer to A, you keep getting smaller and smaller and smaller. Then I'll denote that by the limit as x approaches A from the left side of f of x is equal to negative infinity. Similarly, we'll denote the same situation as a limit as x increases up to A of f of x is equal to negative infinity. And you can do it from the other end. Suppose that as x approaches A, you keep getting smaller and smaller and smaller. And so we say that the limit as x approaches A from the right side of f of x is equal to negative infinity, or we use the following notation. The limit as x decreases to A of f of x is equal to negative infinity. Next, suppose that all of a sudden we peter out and we approach some number. Usually we call this the asymptote, the horizontal asymptote. And so suppose that as x keeps getting larger and larger, my values keep approaching some number L. We denote that as follows. The limit as x approaches infinity of f of x is equal to L. Suppose we have some function where, well, as we keep getting smaller, x's keep getting smaller and smaller, we approach L. Again, this is usually, we called in previous classes a horizontal asymptote. So we say that the limit as x approaches negative infinity of f of x is equal to L. Suppose that as x gets larger, your y values also get larger and larger. Then, in that situation, we have that the limit as x approaches infinity of f of x is equal to positive infinity. Suppose we have the situation where as x goes to infinity, your y values keep getting smaller and smaller and smaller. In that case, we denote that situation by the limit as x approaches positive infinity of f of x is equal to negative infinity. Note that when we're saying these, what we're meaning is as a limit. And so suppose that as x keeps getting smaller and smaller, your y values keep getting bigger and bigger. Then we'll denote that by this situation by the following notation. The limit as x approaches negative infinity of f of x is plus infinity. Next, suppose that we keep as x keeps getting smaller and smaller, my y's also keep getting smaller and smaller. Then we'll denote that as follows. The limit as x approaches negative infinity of f of x is equal to negative infinity. So we have a few more of these. Now let's look at a two-sided limit. So we're going to approach A both from the left and the right. If, as we approach x from the left and from the right, my y values are getting larger and larger and larger, then we say that the limit as x approaches A of f of x is positive infinity because my y values keep getting larger and larger and larger if I approach from the left or if I approach from the right. Suppose that as x approaches A from both the left and from the right, my y values are getting smaller and smaller and smaller. Then we say that the limit as x approaches A of f of x is equal to negative infinity. Next, if as x approaches A, well, on one side, you go to something, but on the other side, you go to something else, then we say that this limit does not exist. So limit as x approaches A of f of x does not exist. We will usually abbreviate does not exist by DNE, does not exist. Oh, okay, so let's do an example. So on page 61 in problems 39, 29, sorry, problems 29 through, 39, determine the infinite limit. Okay, so let's do that. Oh, it told you it's an infinite limit. And so this is problem 38. The limit as x approaches 2, not negative 2. Remember this superscript here doesn't tell us that we're approaching negative 2. It tells us that we're approaching 2 for values of x's, well, in the negative direction. What's the negative direction of x? The negative direction of x is to the left. We're taking values of x less than 2. And so I'm taking values of x here that are less than 2, but approaching 2. Okay, so let's do that. And so of x squared minus 2x divided by x squared minus 4x plus 4. Well, the first thing you could do is sort of the naive approach, which is to just plug in 2. So let's do that in my head. So I'm not going to actually write it down because it's actually an incorrect step. So I'm not going to write it down. I'm just going to sort of speak it out. So if I plug in a 2, that's 2 squared, which is 4, minus 2 times 2, which is 4. 4 minus 4 is 0. So in the numerator, I get a 0. Okay, let's plug in 2 in the denominator. So I get 2 squared, which is 4, minus 4 times 2, that's 8. So 4 minus 8 is a negative 4, plus 4 is 0 again. So I get something approaching 0 divided by something approaching 0. I get, if I plugged in 2, I get a 0 divided by 0. This does not mean that the answer is undefined, that the answer is infinity. What this means is do more work. So if you plug in and you get 0 over 0, do more work, okay? So when doing these limits, think of that as just the indication that you must do more work, okay? That you're not done yet, that you've got to figure out what's going on. So let's do more work. More work usually means factoring. So, well, maybe I shouldn't say usually, but many times when you're doing more work, what you're really doing is simplifying. So let me try to simplify this. So let's factor x minus 2 over x minus 2 times x minus 2. So I just factored this. So I factored the numerator and the denominator here. Okay. Sorry. I'll make it a little nicer. It's still, I keep doing that. Why do I keep doing that? Okay. Sorry. There. Okay, so I want to make the limit here as x approaches 2. So I notice that I can cancel the x minus 2s. And so this is just the limit. As x approaches as x approaches 2 of x over x minus 2. Okay, so let's figure out what this is equal to now. Well, if I plug in something, well, let's plug in 2 now. So now if I plug in 2, I get a 2 over 2 minus 2, which is 0, which is not 0 over 0. It's a 2 over 0. So I don't have to do more work. I just have to figure out what's going on. So 0 over 0 means do more work. Non-zero over 0 means figure out what the heck's going on. And so now I've got to figure out what's going on here. So let's take a number close to 2, but less than 2. That's what this limit means. It means I take a number here that is close to the number 2, but not equal to 2. So let's take a number close to 2, 1.9, which is less than 2. So 1.9 divided by, well, 1.9 minus 2. So that's going to be a negative 0.1. So 1.9 divided by negative 0.1. Oh, that's like a negative 19. Okay. Now let's put in something that's smaller, closer to 2. So something like 1.9999. That's a positive number, divided by 1.999 minus 2. Oh, again, that's a small negative number. A big number near 2 divided by something that's really small. Well, we saw that when we did like 1.9 divided by negative 0.1, I got something that was big, like a negative 19. So if I take something that's close to 2 divided by a negative number that's really tiny, I'm going to get a big number in absolute value that's negative. So this is going to approach negative infinity, because I have a big number, 2, divided by a tiny number. Let me not worry about the sign. I have a positive divided by negative, which is negative. Now I have a big number, like 2, divided by a tiny number, 0.0001 or something. And so that makes the number I'm looking at very large. And so this approaches negative infinity. Any questions about this? In the next few sections, we're going to be a little bit more particular and spell this out in much greater detail. But any questions at this moment? By the way, notice that the two-sided limit doesn't exist. That if I plugged in numbers that were both greater than and less than 2, if I plug in a number that was greater than 2, I would get 2 over a small number that was positive. So I get a positive infinity. So if I looked at the other sided limit, I would not get a negative infinity, but I get positive infinity. Therefore, they're not approaching the same, the right and left side limits aren't equal. And so the two-sided limit would not